Hi, my name is Abdelatif.
I'm Bronson, and this is Lab 11 Diffraction.
Quantitative observations using a laser, a lens with a changed varied aperture, and a camera.
The purpose of this experiment is to qualitatively analyze Fresnel and Fraunhofer diffraction under several different conditions, such as different widths of apertures, double slits, and complex apertures. According to our Fresnel equation, we can expect the Fraunhofer distance to be around 20 centimeters. So, looking at a single slit, we observe the slit width to be inversely proportional to the width of the sinc function. So as we increase the width of our aperture, we should experience a more narrow sinc width. And then observing a double slit, we should see the envelope more frequently, so it's divided. And then we should see the envelope to be proportional to the slit width and the carrier to the slit separation. So as we increase the separation between our two slits, we should observe faster oscillations in the carrier of our sinc function.
When the camera is placed at the image plane, this is the image we see. When we move forward, we will see Fresnel, and when we move backward, we will also see Fresnel until we get to the Fraunhofer.
From the equation for our Fresnel number, we can solve for Z0, our Fraunhofer distance, using the approximation of our aperture size, wavelength, and number of Fresnels.
We uploaded the image of our diffraction pattern for the rectangular aperture. In MATLAB, calculated the plot. Here we can see that the fit is the theoretical data, and the data, the green line, is our data. The plots from the rectangular aperture do match the Fourier transform of a rectangular function. Here is the plot of intensity using the circular aperture. We can see that it fits the sombrero function because the sombrero function is the Fourier transform of a circular function.
Image plane, we observe an image of the triangle. Going in front of the plane, we observe Fresnel fringes. Going behind it, we also observe Fresnel until we hit a point where Fraunhofer is observed. We expect the sides of the triangle to fall off as a sinc function.
Both circular and rectangular apertures. We can see that the variation between the experimental and theoretical values is somewhat high, but our normalized magnitude is 1.
So when we're looking at the circular aperture, we use the sombrero squared function and look at our first maximum and second maximum values to derive our percent error. Our offset was also used to normalize our data, and that's given by this equation.